Okay. Today, along with the lecture, along with the slides and the notebook, I'll be trying something to have a whiteboard, and I think it most definitely will work. But let's see once we reach that point. But in general, last time we were discussing neural networks and how they were deployed within the notebook, right? Now we'll be continuing that discussion. And as a neural networks, I'll just review basically a rough idea, but we'll go over the recurrent neural networks, which is another family of neural nets. Right. So up till neural nets, based on what we discussed in the last class, were there any big questions, like some things which were just absolutely not clear?
Good question.
Mm-hmm.
Okay, so you wrote down the formula for what one individual layer does.
Yeah.
So I think if I expand that formula, I should be able to write out an essentially polynomial equation for the whole group. Is that correct?
Yes.
So
like a very large
equation. I don't know, like 2,000 terms, right? Right? For each node is going to have a term, right? But I can write that thing down. Yes. So we nevertheless talk about these things in terms of layers. But it seems what I'm doing is an optimization over a giant polynomial, but I can pick any other one. Like,
yeah.
Is there an intuition for like why these things have to be discussed as layers? A short intuition.
So one thing which happens, which is definitely not the first idea, but something which I would say as an outcome of this is that if we just make it one polynomial, we are leading up to only one answer at the end of all these layers, right? Whereas sometimes you can take outputs even in the middle of the process.
Oh, okay.
So, but that's a different requirement. For a large number of cases, it's just going to be one. So then one model is a really, really big model, which means the optimization won't work really well. And there are different things you can apply at the layer level. So before this 2012 revamp of neural networks, I think hidden layers was a commonly used term, that a neural net has an input, an output, and then hidden layers, right? Whereas now you just treat each layer as a layer. So hidden layer term, I don't see it being used that much now. I mean, it's just a layer, different kinds of layers, several kinds of layers. So I think it's just more for an easier representation that you have a layer by layer architecture, because there are algorithms. I think distillation is one of those processes I don't remember, which do this condensation because for optimization. That once you have a well-trained model, which is this complete model, you don't want to use it as a layered architecture which moves slow. You want to use it as condensed as possible. And TensorRT is one of those libraries.
So for evaluation,
yeah, while training, you want this layered architecture because of the backpropagation algorithm. But once it is trained, it's just a formula. It's a very large formula. It's just a formula. So then you put it on. TensorRT is NVIDIA's library, which does this, that let's say there's a model you trained using TensorFlow, and now it's well trained. Now for just the inference part, no backpropagation, just using it as a function, it would take the trained model, optimize it, make it much, much faster than whatever a TensorFlow model would be in inference.
How long is that process?
Sorry?
The transformation process.
Mm-hmm.
How long is it?
I haven't tried it myself, no idea. But these are sort of like just small transformations. They themselves are not iterative processes. They won't take that long. You're just optimizing. You have an architecture and you have weights on that architecture. You want to condense it using some particular algorithm. And that process was never really successful. So it's a fast process, the way it's fast. Okay, so this was the feed-forward neural net side. The idea was you have a feature vector, you have a large feature vector, many characteristics basically predetermined, and you want to learn something out of that. That final outcome can be a classification outcome, regression outcome, multi-label, multi-class. Basically, you have this choice of different outputs, but the input was multiple features within one vector, right? So when we dealt with our sentences, we ultimately ended up representing each and every word as a very long vector of 422 length, each and every sentence as a long vector of 422 length, with each position just specifying a word, right? So in terms of capturing the sentence, we were able to capture the words right? That existed in the sentence, but there was something that we could not capture. What was that? In the representation that we used. So each and every sentence had so many words, right? And when we represented it as a large feature vector, we had the number of words, so we could contain that information, but
not when they occur.
yeah, so the order, the nature in which they occurred, the sequential nature was lost, and there was just no use. There was no way in that particular architecture we could specify that information. There is this notion of which word is coming when, and then as per the network, word at position 1 is the same as word at position 10. There is no weight of position, right? So is there an architecture that can leverage that piece of information and still work in sort of the end-to-end way as we discussed earlier? That brings us to the family of recurrent neural networks. So neural nets broadly can be categorized into 3 families. One is the feed-forward neural nets, the ones that we discussed. Another is recurrent neural networks, which take care of the sequential nature of data. And the third are convolutional neural nets. So convolutional neural nets are very fast and highly optimized, mostly used for images, but that's not their only use. They can be used for sequences. They can also take care of ordered information. But the real property of a convolutional net is that they can work on they don't need the full connections. So a fully connected neural net has all the links, right? Each input is corresponding to is being connected to a neuron in the next layer. Convolutional nets don't have this case. They can actually operate on smaller segments and then repeat that segment of weight. So that's slightly more complex in terms of a space of networks itself. So I won't be discussing that at all today. Today I'll stick to another complex category, which is the recurrent neural nets. So now, let's say we are back to the same input, which was a sentence, and we don't have any feature vector or anything. We want to send that sentence through a neural network and try to learn the same outcome. But in this case, our input is not at all flat, so to say, like it's not a flat vector. What is it that we can do? How can we represent our input? And how would we structure a model which would basically take that information and use it? You know, the IID property, like independent and identically distributed. When you look at your normal data set, you treat it as IID, that everything can be separated independently. And if I select one feature, my selection of other feature is not really dependent on that. That's an assumption that we start with. But if you have a sentence, if you have a sequential input, that assumption within those elements doesn't even exist, right? So each and every word in a sentence is connected to the previous and the later words, right? There is this correlation within the sentence that cannot be, you can choose to avoid that piece of information and not deal with it, but there is this information, right? The sentence, how do we capture the information? If I send the sentence capture, do, be, how, like if I just jumble these words around, the meaning will change completely, and that information is important, but is not sent to the model easily if you just flatten up things. So maybe a normal neural net just takes a flat vector. So recurrent neural nets instead can take sequence, which is several vectors, maybe like several inputs ordered by time. Time is like normally used, but ordered in general, like one comes after the other, and that sequential property is important. So you can consider them this way, and that if you ignore this piece, a normal neural net, if you represent it as a block, just takes xt, the input, and produces an output called ht. But now, if your architecture can take that stepwise output back as an input again, and use that information going forward, so you can probably send in a sentence first word, right? Learn something from the first word. Use that learned thing along with the second word to learn something from the second word. But now it's not just learning something from the second word, it's first word and second word. Going forward, third word takes more information, right? So at every step, you're forwarding this information. So expanding this thing, we can see it as your sentence is split into different words. Each word is going at each time step. And at every step, you're learning something which you can see as itself, like there's an output, but you are also sending that output again and calculating with the second input. So now, earlier, your output y was a function of the input x. Now, in this case, your output y is a function of the input and the time steps. So at every step, when you're like yt is equal to, or ht is equal to a function of xt and ht minus 1. Like at this point, when I'm calculating ht, this is a function of xt and xt minus 1. Sorry, ht minus 1. There are two inputs in concern. You are using whatever is the real input. These x's are known, but h is are being learned. So you're using them at each and every step going forward. By the way, this link connected on this would be one of the best, like nicest link I've ever had for learning LSTMs. This person is Chris Ola. He's, I think, right now a scientist at Google, but he specializes in writing tech articles which are easier to understand. Anyone can read and really learn from those. Really recommend learning about LSTMs and recurrent neural nets using this link, and it would be on the resources.
I have a couple questions on this body now.
Mm-hmm.
So the arrows going between the time steps?
These?
Yeah. Okay. So my arrow from X into A, that's a vector of size 422 in our last example.
Mm-hmm.
And from A to H is a vector of size 6. So the arrows between the A's is a vector of what size?
This?
Yeah.
It's exactly H2. H2 is being sent here. So it's the vector of size 6.
I don't know. I could 422, right? Like you can treat this as essentially additional layers in your network for which you have input in the middle of the layers, right? Rather than only at the start, right? And then they could be bigger or smaller, or there's no telling, right? But by convention, they're normally the size of H. Or they could
They have to be. It's exactly H. The thing that I'm forwarding is nothing else but H. So let's see it over here.
I don't see any fundamental
X
reason that has to
zero.
be true, but okay.
Yeah, but that's the formulation of the recurrent neural net itself, that what you're sending to the next time step is the activation of the previous time step. So,
Okay. It just looks like more layers in the network.
A is the same. A is not new. So
A is the same.
Yeah, see, that's why these are equal. So that's just expanded over time. A remains the same.
Actually, can you, just for the sake of
Mhm.
can you give us like one sentence? So I had a sentence like, I love dogs. Then X0 is I.
Yeah.
I put I in, and with HO, I get out
A vector.
a vector,
Yeah.
right? But my XO is just the word I.
A vector of I.
It's the
A
vector
vector
I,
representation of
which
I.
Okay, which would be the 422 vector that has, if it was my very first word in my whole dictionary, it would be a 1 and then 0, 0, 0.
Absolutely.
So I throw that in and I get out my HO. And since I is not inflammatory in any way, I think I is one of the soft words, so let's just disregard that. Then my HO would just be all zeros.
Yeah. HO would be whatever it chooses to learn. HO is not your
But
output.
let's give a real example. I want a real example that I can extrapolate out for myself, like how I would generalize it.
Right.
It's easier for me to have a specific example and then I can generalize.
Yeah,
If you can generalize,
let's
I
say
can't really.
HO will have most of the zeros, like most of the neurons, which are the ones determining whether it's abusive or a hate content, right? Those neurons, let's say, are 0. But maybe some neurons are there, which are sort of keeping the information. One of the words that appeared so far was I. And that neuron is 1 now, because it got this information that I has appeared. Because the second word that's going to come over here needs some information of what happened before that. That's the whole point of going into RNN, right? So in our at 0, maybe any activation related to the final outcome of detecting hate was 0, but there was some information that the information element, like the bit in the vector, that contained information of I having occurred already, is now 1. So now H0, when it comes over here, and I send, what was the second one? Love, right? Love comes here. It has this information that I was already there in H0. Through H0, it has that piece of information. Whereas through X1, it has this information that a new word love is there, and it will try to learn a new representation. And maybe within those, and now H1 will have maybe there's a bit which contains the information of I and love having occurred in a sequential nature already. That will go to 1.
And we're still talking about an H that is a 6 spot. Vector.
No.
Now
we are talking about H being any randomly sized vector. Okay. We are not producing that output right at this moment. H is
not 6.
H is not 6. H is not that. Oh, that's why you said.
I'm like, why is it 6?
Okay.
Keep saying there's a spot for this, a spot for that, I'm
this,
right? I'm like,
this is what has to be 6, right?
Yeah.
In a normal neural net, this point had to be 6, right? In our case. But the layer that you're looking at is just, let's say.
So you're saying I might be recurring somewhere in the middle of this.
Yeah.
Right.
Okay, and A, what's held in A is all the coefficients for all of these things. So A is not changing.
A is not changing.
Right? So what's happening is, what you're saying is, essentially I'm taking the output of a middle layer, and then I'm feeding that back into the inputs of the next layer, but I'm not changing any of those coefficients.
You're still in the same layer. This is still the same layer. You see?
Right.
Let me.
And we're actually, could I have a vector that instead of, this may be stupid, but that had vectors contained in it? Could I have that?
Just a second.
Because that would then give me order. Because if I was my first word, and in the spot for I, instead of just being able to put the word, the number 1, if I could put the number 1, I like have a vector there. So the number 1 would be the number of recurrences, and then a vector saying in what spots I saw the number 1. Like maybe that way I could have order and occurrence. Is that possible?
I mean, it can choose to learn something like that, but what you want is it to ultimately. Let me.
I think
can it only choose to learn what I want it to learn? Because I always operate under the premise that the computer is my stupid friend, and if I can't in some way do it once, with an easy example, I can't teach it to do anything.
Okay, that assumption was valid until you were in that ML space. In ML, what you want is that you're showing something to the computer, and you want it to learn now.
Right, I know I want it to learn, but I have to teach it how learning happens.
Yes.
So I have to be.
But not what it learns. You see, exactly is that you want to teach it how learning happens.
Right.
But you do not choose what it learns. In this particular space, like in the way neural nets work, is you're not choosing absolutely what it learns. I mean, you're nudging it more and more in terms of what you want it to learn, but it's learning something what it can understand as a representation over different combinations, right? So we had our input I, love, dogs. Okay. Yeah, it might. Sorry. No, my handwriting is bad. That's a given. But okay, so this is the input, right? Now this this becomes my x0. This becomes my x1. This becomes my x2. Now, the way we defined it
as a 422 vector, right?
At this point, let's say it's nothing. It's just an integer saying this was my first word, this was my second word, this was my third word. Right? Okay. So that's a state which neural net won't understand. So now,
wait, you're going to encode this. This matters, I think, what the parameterization is.
So
it does. Rather than inputting a vector that's all zeros with 1, 1, you're going to input actually the integer 312.
No,
word dog.
Oh yeah. Like
let me explain. So to the layered architecture, now this is the RNN layer, right? And let's say this layer goes down to like a dense layer, which is the normal layer, and now I have my 6 outputs. Okay. So slightly more complex than what I've already discussed. But what I'm saying over here is that let's say this was 1, this was 12, this was 34. Okay,
Right.
these were just
Okay, good.
integers. Now, before I enter them into the neural nets, I want to vectorize them. So one of the ways to do that is what we discussed, like what Suzanne said, is that you can have sort of this 422 sized vector, which will be, and like let's say this is 12th position, so love would be represented as this, right? This is just one of the possible encodings in which you can send the information. So it's commonly used and it's called one hot encoding. You have a big vector of all zeros and there's one position which is on, so one hot encoding. But that's just one of the examples. An example which I'll show in the code today is called embeddings. So since it's a since this class is discussing neural nets within 2 weeks, everything has to come together. But embeddings is a way to represent a piece of information as a vector. When we do this kind of information, right? A good example is, so let's say in our 422 words, 12th was apple. No, let's say it was apple. Okay, so this is now 22. Yeah, so 12th was apple, and 101 was like 101 was orange. Okay. Now, if I look at this notation, if I try to visualize it in a certain way, how can I visualize it? It's a large vector space of 422 dimensions. And in one of those dimensions, when it's 1, that means apple. Whereas in like a totally different dimension, when it's 1, it means orange. Semantically, I know there is more to that. I mean, apples and oranges, even though they are two different words, they are two different symbols in a big vocabulary space, in reality, there should be some meaning between them, right? And if I have a large enough corpus where words appear together, shouldn't I be able to learn maybe which words are close to each other in the real language itself, like in semantic nature as well? And the ability to define them as vectors now with dense vectors. So these are sparse vectors, right? You have a really large vector where there are so many zeros and there's a 1 somewhere. That's a very sparse representation. But maybe if we can sort of have a small vector space where all the words which are fruits appear somewhere close, right? So the vector value, like the final vector position of those, so if we have like a 2D space, then maybe fruits are over here, maybe animals are over here, and you sort of.
So in which case, instead of looking at your data as you get it, like you did your example, looked at the first word, and obviously you've never seen it before, so that became a 1. And then, like, let's say we get further in and we look at that word and we go, have we ever seen it before? Yes. What number is it? No, it's a new number. Instead of doing that, we look at all the words we have, we categorize them as different things, and then we kind of group the numbers of like things close together. Is that kind of what you're telling me? So we take all the words and we kind of reshuffle them before allocating numbers. So that apple, and even if it occurred earlier in my text, and that's why it originally had a 12, and orange occurred later in my text, which is why it had a 101, we reshuffled it and maybe made apple 12 and orange 13, or apple 50 and orange 51, which doesn't really tell us when they occur in the text, but it tells us that they're similar.
They're similar.
Right?
Yes.
Okay. So in that way, though, you have to read in your entire text and then sort of categorize and resort it before allocating numbers.
Yes, but that's not what you want to do when you want things to learn by themselves.
Right.
So you consider this kind of situation to be your output, and you build an architecture which ends up learning something which is similar to what you want, right? Which ends up learning some things where all the words which are similar will be in a similar vector space, whereas words which are different will be in a different space, and the vector, which is the final representation defining them, will have more knowledge than just the symbol of like a 1 there here and a 1 over there. So that's the.
So then the fact that they were near each other would imply that they were similar, especially if we had a way that we always packed our groupings. Like we had fruit as 10 to 15, and then we had 16 was always blank and would never, never, never occur. And then we had 17 through 25 was office manager, right? So proximity, having something really close to each other would tell us something about, it would tell us more than it just occurred. It would also tell us that they were similar.
Yeah, so that's the hope, that you want to learn something like that. So, which is where I drew this like layer, which is called embedding layer, right? So these are more of the terms of the libraries that you'll be using, PyTorch and TensorFlow, but they are good to understand things as well. But now the job of this layer is to learn a reasonable representation. To start off, it's totally fine to use one-hot encoding, but a dense embedding more or less will give you a better result if you have enough data to train that though. Because I don't want to force any information on my data set. I don't want to group the fruits together myself. I want them to be grouped in a way that's good to get a good outcome, right? I want my data to be categorized by itself. I want those vector representations of each and every word to be learned, not to be like forced. So this one.
It's probably a stupid question, but how can it learn that an apple, and because you could say, I love apples, and you could say, I love dogs, and you could say, I love oranges. We know that apples and oranges are fruits, and that dogs are animals.
Yeah.
But how?
Because your data might have, I ate an apple, I ate an orange, but it won't say I ate a dog, right? I mean, so
it looks at different kinds of things based on,
So
it doesn't have to be right.
Yeah.
It only has to be some embedding that makes it work.
Exactly.
Right.
It doesn't have to be right.
No,
you're
thinking they have to be put together, but no, it has to be some dense embedding, which makes the learning efficient, so that you predict your 6 outcomes in the end.
Yeah. So
that's the only thing that makes any difference to it.
That these are words that always occur after the word love, and not that they're all fruits or all.
Yeah, exactly. So anything that helps you reach the outcome is what the model should learn. And the core idea in a neural net is you don't want to force feed information. You want the model to learn things, deriving things, right? So this representation in a dense vector would be, instead of 422, let's say it would be a 32 size vector with like 0.5, 0.3 and different kind of values. It's just a dense vector space where points may have a semantic relationship between them. Depending on your data set, depending on your problem, you can also come with pre-trained embeddings. I won't go over those right now, but you want a denser representation of each and every word. That's the idea, right? And now that vector goes into the RNN. So I'm clearing the board and changing the color to black just a minute. Okay, so now when we go into the LSTM space, into the RNN space, we have, so this function is same, right? This fn is same, it's the same function. ht minus 1 is the output coming over there, right? So what we are doing over here is that this is just one layer of a neural network, right? So you can represent it as the neuron kind of diagram, which takes an input vector, learns an output vector, but then doesn't move on to the next layer. So in a layered architecture, in like, let's say, in a layered architecture, we had our input, right? This is our input, which was a sentence. And then we had some layers, and then we had the output. So when we do a free forward network, we go over here, then we go over here, and we go to the output, right? Whereas when we do a recurrent neural net, we go over here, then for some time we keep on going over here, then we go over here and reach the output, right? So that's the movement along time, like time steps. And similarly, when we perform our update operation, which is the backpropagation, it's gonna go like back propagate the error here, right? And then it's gonna come over here, and then this thing, it's called like BPTT, back propagation through time, which will sort of back propagate the loss over here. So now the key, this is the key in learning the special kind of cell, is that even though the same function was giving different outputs, right? It's not updated just vertically downwards. It's updated with the order information that went into it. So that's why it moves through time. So you're going upwards in a neural net, learning layer after layer, but when it's a recurrent neural net layer, you're spending time on that layer learning horizontally. So that basically is the process of going through a neural net. And now these x's are just vectors. The h0s are also vectors, and these are hidden vectors. Like these are somewhere within the larger layered architecture. And now you have, instead of one vector, right? This was like when we were treating the feed-forward neural net case, there was like one vector. And then there was this final one output, which was like 6 size vector, but you just had one vector. Right now you have too many vectors. And even at this stage, you have too many vectors. So you want to choose a certain method of reducing down to one vector going upwards. So generally, if you have a recurrent neural net, what you would do is you're hopeful that all this information is well contained and like going from here, going from here, going from here. And then the final last time step, whatever activation it resulted into, HT, is the one that you take forward. That's one of the common practices. It doesn't have to be this way. I'll go over some other ways that we can use, but at this point, let's just assume that once you pass something through an LSTM, this HT is the single vector output that goes out. If you want all these vectors, you can have those. You can have T number of vectors, which will, and the number will be different for each and every sentence because each and every sentence is of different length. But if you want just one representation, for now we are assuming that representation to be the last one, HT. Okay. An input, a complex input, an ordered complex input of a sequence comes in, and then you move forward to sort of learn beyond this. And this piece of information now, HT, can just go on to another dense layer or the layers on top of it and move in a normal way. So the total, like the main layered architecture now would be that you have your input, which goes to an embedding layer, which sort of learns the vector representation, right? And this means that the input is sequence. So multiple arrows just means that the input is sequence. So after embedding layer, you have the same length of sequence, which goes to an RNN layer. And now we are saying that at RNN layer, we are just going to take the last time step. Now you just have one vector. And then it can go to a dense layer. And then maybe let's say the final output layer, right? Which gives us 1, 2, 3, 4, 5, 6. 6 values for each and every class, right? So this is an architecture which will take the order information. Now, how to send that in the code? That I'll go over in a while, but up till here, are there any questions? Yeah.
So if I had a fixed input, let's just say I have a sentence of 5.
Mm-hmm.
My understanding is equivalent to having my input be my vector times 5 and I add 5 layers there, right? Just expand out the layers.
Yeah.
And then put some constraints on the weights so that I'm required to have the same weights in each of the 5 layers. Right? Because you reuse it, right? So there's a constraint on what the weights are, right? So it's something less general to actually just sticking like a layer step. I presume people like it because it's more likely to solve.
So yes and no partially. So if we didn't have the embeddings, if we just had like clear vectors representing our input already, right? Now, then if we force the input to be a fixed length, so every sentence can only be 5 words, and we have this single vector representation of each and every word, then maybe I don't need an RNN. I can just always flatten them out to be a longer vector of like word 1 vector, word 2 vector, and these 5 vectors, so 5 times, right? And now this input representation that I made already contains the order information, because a net can learn that this is the way these words are always occurring. But first of all, it's not expandable. You cannot increase the length. Now you have a fixed vector size, so you will have to force your data to be 5 sentences. And second is that the correlation between different words occurring after one another is now again forced on a flat vector. So you're not really learning it in those steps. The backpropagation through time is never going to happen. It's a flat backpropagation that is happening. Right?
Too detailed. I'm not going to
Any other questions? Yeah.
So I had a question about the non-propagation through time.
Mhm.
You're taking one layer, passing the they're running, and then the number of times you run through is very long.
Mhm.
So how do you work backwards through that? So you get an H0, and then I'm assuming you don't pass that up, so you don't have that propagation on that. So
You do retain that information. You have to have that. Maybe you don't use that in your, so that information, that HT is a formula of HT minus 1, right? HT minus 1 does contain some information of that previous time step. So if I have HT, I know the formula of creating HT. So if I'm backpropagating through that, I know how to go to the information of HT minus 1. And HT minus 1 knows that it came from XT, and right? So you are actually going back with that information, and you are holding some information. I mean, that's why these are heavy and long processes, because you are holding that information. LSTM recurrent neural networks are, I mean, you don't want to use them all the time. That's just a simple way. They are heavy, they are expensive, they have this additional time information that they want to retain, and it takes longer to train them. It takes way longer to train them compared to a feed-forward net. But even compared to convolutional neural nets, which I'll cover next time, but recurrent neural nets are heavy to train because there is so much more information. You are performing 2 directions of backpropagation. Okay. Any other question? So let's take a break now, and after that I will cover LSTM very briefly, because this is an applied ML class, so I want you to be able to use things, maybe not understand all the equations underlying it. So LSTMs are very, they are the tools that you're going to use when you use recurrent neural nets in the long run. But I'll go over them in short, and then we'll explain how to use them. Okay, so recurrent neural nets, that's what we have covered. And what this example shows that the activation, remember there was an activation function at every neural net. The activation function we were using was tan H in a normal net. But now there are several problems with recurrent neural nets. So read this blog for more details, but it's called vanishing gradient problem, where once you have a long sequence, once you keep on going with the information, the value used to update, right? The gradient which is used to update becomes smaller and smaller and smaller the deeper you go. And ultimately, for longer sequences, you really are not able to make any kind of update. So in 1997, a new model was created, which was LSTM, long short-term memory, which tries to hold long-term dependencies. So if there's a very long sentence and a word that occurred, let's say at position 3 has importance at position 100, these models are good at retaining that piece of information. It's fine, I mean, he knows. Like he would not like if we stop the class. So. Okay.
Because I really couldn't hear what you were saying. I mean,
so standard recurrent neural nets experience a problem of the vanishing gradient. Read the blog post to get like a quick overview of that. But LSTMs have a solution for that by using a gating mechanism. they were first in 1997, and then in 99 there was another modification made to them using there's a concept called forget gate, and from 2012 onwards, or maybe 2008-9 onwards, they started resurfacing again, and now they are the standard for anything with neural nets, anything with recurrent neural nets. Like there's another variant which is a lightweight LSTM, which is called GRU. It's a gated recurrent unit. Those are also good, but LSTMs for your neural machine translation, for different tasks in natural language processing, they are the standard. I mean, you want to use LSTM, not a simple neural net, because they work very well with longer sequences, and the more and more you go into detailed text, you want longer text to be taken care of. Yes.
Just to clarify, when you say LSTM, what exactly are you referring to?
Oh yeah. So remember, I was making that A, which was repeating. It's called a cell. So a recurrent neural net has a cell which has several neurons inside it, which is just a neural net. But for the longer architecture of a recurrent neural net, you can call it a cell. And that cell was a standard formula, y is equal to wxt plus wht. It's a standard formula in a normal recurrent neural net, whereas in LSTM, it's a much more complicated formula. It has 5 equations to it precisely. And we can go over those if we have time later on sometime, but for the sake of usage, what I want you to understand is that it's still a recurrent neural net. The cell has changed. The formula that you were using on xt and ht minus 1 has changed. And one more thing which has changed is that earlier we were saying that we are only providing this ht information at every time step, right? In LSTM, we're providing 2 pieces of information. One is called ht, another is called ct, like cell memory. So while this is a good diagram, it's not the most explanatory one. So I'll post another link to the better diagram, which has more relation with the gates. But and the equations move in this way. You have a forget gate, you have an input gate, and you have an output gate. There are 3 different gates, and a gate is basically just like a gate in a digital circuit. You have 0, 1, but it's a soft gate, which means you don't have a step function like you have a sigmoid function, as I explained earlier, right? Instead of just saying 0 or 1, you are holding a floating point number between 0 and 1, which sort of determines how much information you transmit. So the gate is in charge of that. And the 3 gates are input, forget. Forget gate does not take 0, 1, it takes -1 to 1, because I forget, which means it can be forget or remember the way you want to learn. But what we are saying is, we had some memory from the previous step. How much of that memory should we use? That is more or less the idea of forget gate. So the gate in itself is still a sigmoid because the gate is there, but the way you use it to update cell memory is using a tanh operation, which means -1 means clear up, 1 means retain everything, and somewhere in the middle. So it gets more and more complex if we explain the LSTM, but for now, just treat it as a black box that you want to use it as your RNN cell going into the process, and at every step, instead of just transmitting HT, you're also transmitting CT, and every cell will use those 2 pieces of information instead of 1, and XT is always going to be used anyway.
So HT is still a vector.
Everything is a vector.
As well. So
HT and CT are same size vectors.
Okay, so -1 is clear, 1 is safe. What does 0 actually?
That's basically if you want to clear up all the information that was there. I'll go over the formula to explain to you. I'll go over the equation related to it. You see these signals, right? They are 0 to 1. The tanh is -1 to 1. But I'll explain to you with the equation later on, maybe after.
The connection between a cell and a layer. Does a cell connect neurons at different layers? Or is it all in the same layer?
it's in this, it's still in the same layer. A cell is a way to break down your layer into time steps. Right? So yeah, the thing that you refer to as a layer, it can be a layer of time step number times use same cell. So cell is essentially that single component, but you're using it within a recurrent architecture. So the cells can be changed. The three most famous cells are simple RNN, GRU, gated recurrent unit, and LSTM. So this is LSTM. And now let's move back to the code that we were working on so that we can see how to use this. Okay, can you just check if the code is visible?
Yeah.
Okay. So how, first of all, I have to upload these things. I will upload the two notebooks on Google Drive as it is. That's step one. But then what will happen is that this data, won't work. So it will be your job to download it and download the data from this website, because you have to sign the agreement. Like you cannot just, it's not a link that would work. You have to log in to Kaggle. There's an I accept, sort of like understand the rules of the game, competition, and then only you can download the data. So that's a step individually everyone will have to do. But once you have downloaded the data and it sits in a directory with all the CSV files, then running this on top of it would work. But to give you access to the code, I'll publish it today itself. What I did over here is that the notebook that we went through in the previous lecture, we created, each sentence was represented as a bag of words. And then that bag of words was represented as a feature vector, right? The 422 length. Now, and we know that we could not retain the order information. Now we want to use absolutely the same framework, the same ML pipeline, just make changes at the points where we can add this order information. So we start off with the same way. We get the data, right? Now to extract the features, we still need a vocabulary, right? So no difference over there. Up till creating a vocabulary, we do the same thing, right? So we have a vocabulary. The frequency-based removal and stop word removal, all of those, it's always a matter of choice. It was a matter of choice even in the earlier case, right? And it's still a matter of choice. So let's say we make all the same decisions. We are limiting down to the same set of 422 words, right? And now we have that. Now this is what we did in the earlier case. We made each and every text in our dataset to be a, okay, let me ask this again. What was this? Doc to BOW?
Regular words.
Okay. Yeah. So that was each document being represented as a bag of words, right? And now instead of that, you're doing doc to index, which is index sequence. So what this looks like is, now each and every sentence looks something like this. And why are there so many 422s? Because what I told this thing is that the index of the unknown word. So now since we filtered down to a very small space of words from 2337 unique tokens, we actually went down to 422 unique tokens that we want to use. So this means there's a large number of over 2000 words which will be just unknown, which are not a part of the vocabulary. So we represent all of them with just a single value. And in this case, it's an easy thing that, like, from 0 to 421, we have the values, we have the indices, so 422 goes to the unknown. So whenever in a sentence, whenever passing through a sentence, you have an unknown word, you will say 422, otherwise you'll give the index. So this representation gives us all the sentences in a sort of long sequence, and the length of the sequence is same as the length of the sentence, right? So up till this point, is it clear how we change the initial representation? Each and every sentence from our data set, each and every comment from our data set is now being represented as a long list of words. with each position determining the integer index representation. So in the architecture that I was drawing, input to embedding to input is this, right? So now we want to create a feature vector which goes to the model. So this step, in theory, you don't need this step, but in practice, you always need this step. Is that while an LSTM would take variable length, if we want to train an optimized method to do that, we always send data in batches, right? So we are always sending multiple sentences at once to train. Now, if those sentences are of different length, then the batch is not really a block. I cannot optimize on top of a GPU. Always think of this way. If things can be represented as a block, which means there are fixed boundaries, fixed edges across every dimension, then you can put it on a GPU and expect it to do really, really fast matrix multiplication and you get better results. If you have variable length, by default, you don't have a block, you sort of have a stair kind of viewer, right? That, how do you make a block? You do something called padding, which means take a fixed length, which is your largest length. That largest length can either be the longest sentence in your data, in your batch at least, or it can be a fixed length. Let's say you just don't care about words with sentences which are longer than 50 words. I mean, you force the information that you need to be just up to the 50th. So that's a choice. You can always have max length to be of the longest sentence, but you can also restrict it to a certain length. But now by doing that, you at least have a maximum, right? That's defined. How do you fill up the empty spaces? For that, padding means you are defining one particular kind of token that when you use that, it means it's just a padding word. Don't treat it as an information or learn to just ignore it. So one is telling explicitly to the model that ignore it. Another is hoping for the model to learn that it will ignore, but padding in both cases is a tool to sort of fill up this empty space of information. So now you can have your block architecture, which will be the optimized calculation, while still being able to hold the ordered information. So over here, what we are doing is corpus up till now was a list of these different line sentences. We are pre-processing that sequence with another function from the Keras library, which is called pad sequences. You send it a corpus, which means different sentences of different length. You say where to do the padding, whether to pad after the sentence or before the sentence. You can make both choices. So post means add the pad values after each sentence. And what should be the pad value? I'm saying len of dictionary plus 1, so 423 in our case. I just use 423 as that extra padding value. It's a conventionally you would use 0 for that, but just to explain that it doesn't have to be 0, I sort of use this extra value kind of thing. But you want it somewhere within, so you still have a limited length of your vocabulary, right? It should be an integer in an indexed vocabulary, because when the model goes on to the next layer, you want something to be like you want a fixed length within which you're capturing something. Yeah.
Okay. Okay, sorry.
Okay. So now, as a result, what we get is that in our case, the longest comment was 312 words. So we have this 312 size. Now, let's say we wanted to limit it to 50, right? Not taking. So there's a parameter called max length. If we set it to 50, then now sentences which are smaller than 50 are still the same essentially, but sentences which are larger than 50 are cut down to the first 50 words. That's just a choice you would make. I mean, in some cases, if you get good enough results by doing just this. For example, if you are processing a data packet, you know, it has a header, right? The data packet in an IP, it has a header, and if the information of header is enough to sort of learn whatever you want to learn, you don't need the payload underneath. So just that much information is good enough. So in different kinds of cases, different lengths may be useful, and If you really want, like if you don't want to waste any information coming in, then you would just retain up till, if we said max length is equal to none, which is the default, you would have the longest length. Okay, so now every sentence is represented as this sequence. So earlier we had it as a single vector. Now we have it as a sequence of integers, which means this piece of information has the same dimensionality so far, but when it goes to the recurrent unit, we will need to represent it as a larger vector, as a larger tensor, which means it has one more dimension, because each of these indices 1, 0 are ultimately going to be represented as a vector, right? So far this is our input data, but now, going forward into the model, we will have to make one more step. Target vector remains the same, so we use exactly same approach. Train, test, validation splits are all the same. Now in building model, these two were our previous models, right? They would take a they would take a vector and then process it using the dense layer. These two would take a vector. Now, when we want to build a sequential model, we do something like this. What this means is, now the input is, first of all, of variable length, right? So you're not saying that it's a fixed length input. You're saying none, which means it can be a variable length input. Up till this layer, what is the input? It's a integer sequence, right? That's the input. KL.embedding is, it's an embedding layer. So the representation that we want to learn, the dense vector that we want to learn per word, this layer is essentially giving us a lookup matrix. So treat it this way, that for each and every word in those 422 words, you start off with a random vector of 64 size, right? It's a dense random vector. That's how you start. And you start using that value going into the model and keep training the model. And when you are training the weights, you're also updating this vector. And the hope is, with good enough data, you will learn a dense representation of each and every word, which helps you derive the best final result. That may end up in similar words grouping together, but that's not the objective. The objective is still the same. You want to perform the best multi-label classification. Doing that, whatever is the best dense vector representation for each and every word is what this layer will learn, right? Now, on the second step, you go to an LSTM. So now this activation is not really required. If I remove it, that works. But up till now, what happens is that this KL.LSTM, KL is always keras.layers, so no confusion over there. LSTM will build a recurrent neural net layer. The input shape to LSTM is not the same as the input shape to dense. Dense was taking batch size, and vector, right? That was a 2 tensor. An LSTM takes batch, time steps, vector. So it's a 3 tensor. So since we haven't defined how long our sequence is, that is none. The shape that this thing will take would be none, none. And what would be the third value? What would be the feature vector size that this LSTM will get in this case? What was that?
Wrong answer.
No, I think it's right. 64.
64.
Why is it wrong? Why was it wrong?
Well, because I got no reaction, so I thought.
Yeah, that was the idea. Just check. 64, because the embedding layer is representing each and every word as a 64 dimension vector. So LSTM layer gets none, which is the batch size, none, which is how many words, and 64. Each word is now a 64 size input vector.
I don't understand why you had to get rid of the activation.
It wasn't like.
It has to be something nonlinear.
Yeah, there is an activation, but
There's a default activation.
the default is always there. So the reason is that it takes 2 kinds of activation. One is a normal activation, another is a recurrent activation.
Okay, it seems like you better do something. If it's linear, then I'm sure.
Yeah, it's not linear.
Somehow, it has to
Yeah.
be some non-linear on each step.
You can sort of do it. Okay. It uses an activation by
Okay.
default. So everything, yeah. So an LSTM layer by default uses an activation, which let's look at Keras library. What is it using? I think it's using sigmoid.
It doesn't matter. I just, it was a concept that didn't make sense for us.
Yeah. Now let me actually give you a look into this. Where is LSTM? The LSTM's activation by default is tanh. It's using a tanh by default. Yeah. And then it has another recurrent activation, which is the hard sigmoid. So, and so it's a sigmoid. It's just instead of performing the exponential, you are sort of fixing some values instead of the exponential. But that's just to optimize. Coming back here, let's just set it to tanh to match the same. But you have your LSTM, right? And you have your dense layer. So by default, remember I said we can take different time steps, or we can just take HT. So by default, if you use this, it's going to take HT. So that's why the input to this layer is going to be 3 tensor, but the output is going to be 2 tensor. So if we draw the model, why didn't it? Oh, sorry. Yeah. So if we draw this model, it looks like this. The input is none, batch size, and a variable length. And then the embedding layer gives us 64 size vectors. The LSTM layer now again boils down to sort of single vector, which is a 128, because that's the size of the vectors that we are getting out of the LSTM layer. And then you have your same dense layers working as before. But what if we wanted all the outputs at the LSTM and sort of wanted to perform another kind of operation on them? So even that is possible. You can just have return sequences is equal to true. So now, technically, it will, let's see if it even builds. So now I'm gonna make a faulty thing because it should ideally not work, but I don't know if it would build up till here. Oh, it builds. So see, now this LSTM is giving me time step number of outputs. So when I will run it, it will break at the end because now I'm performing dense over each of them individually. But my output, the real output, the target, did not look like this. It looked like none 6. It did not look like none 6. So when I run this model, I will get an error. But you can make a model with all the outputs coming out and then performing the layers on top of them. But then these are still not recurrent layers. They will just be the same layer. The same layer will get updated. They won't have the horizontal movement. So another way that I commonly use is to perform a max pooling operation on top of the results of LSTM. So what that means is and now when we perform this operation, we again come down to a 2 tensor, but you can see that there are no parameters of this operation. Because what a global max pool operation looks like is you have a large number of vectors of same size, right? Where's the job? You have the sequence output is like this. And 0.3, 0.4, 0.8, 0.2, and many such. Okay, that's it. These were the outputs that you got out of your representation. Now, max pool operation on top of these says that you want to derive a single vector, which is obtained by performing a max vertically along each index. So the max pooled output of this vector sequence is basically 0.5, 0.4, 0.8, 0.9, right? because you're just doing the max at each and every vector position. Similarly, there is something called average pooling, which will do an average at each and every position. But the idea is that you still get the same size vector, which is an aggregation of the vectors underneath in some kind of way. Max. So you're pooling information going forward. You want to reduce the amount of information that goes forward in some smart way, and max pool surprisingly works really, really well in most of the cases, because it's sort of, you have a wide vector space, you're going max along everything. So within a convex architecture, you are taking care of the extremities and then reducing them. I mean, that's a way to look at it, but max pool is one more approach of taking a single vector output from your LSTM instead of multiple, instead of just taking the last time. So that's just another variant we can create for the model. But now this architecture takes all the information, right? It takes each input as a sequence of words, integer sequence of words. Within itself, it's training this lookup, which will convert each and every word into a sequence, into a vector. So now you have a sequence of vectors going in through the LSTM. And since you are returning sequences, the output is again a sequence of vectors, but then you are performing a max pool operation on them, boiling down to another single vector. That vector goes through a dense layer, another dense layer, and in the end you have these 6 outputs, 6 probabilities for each layer. So that's just one example of a sequential model that you can create. And this is what it looks like. You have an LSTM, you have a max pool layer, and then you have a final dense layer. Okay, so with this thing, do you think I would need to make any more changes in the training and optimization code that we had from last time?
So it's been retrained since last time? Or this is the way that we would retrain?
So it's a new model, right? So we have to retrain anyway, like we have to train something new. But the way, approach that we took on our previous model,
Oh,
do we need to change the approach?
well, you could do more iterations.
That's just a, yeah, we can absolutely do more iterations. But I mean, within the code, do you think any other change is required? So
You got 3 instead of 2 somewhere, so I guess you need a parameter somewhere where you got 3 inputs instead of 2. I have no idea where, but now you have this time thing.
yeah,
Well, there should be a time thing somewhere in your training also.
right. So that's a fair point. But since we took care of things by making sure that the input was still same size and the output was still same size, right? Input is still a vector, and now it's a vector of integers, and in the middle of the model, we are sending it through an embedding layer, which is in charge of doing this dense representation, which is, since we are doing the expansion over here, in terms of the model input and output, we don't really need to change much. So, and that's another advantage of using libraries like this and sort of building a modular code, that you can, once you start on working on a real problem, you want to build as many architectures as you can to sort of reach to the best one. And you don't want to change the code or gather data and the training, optimization, evaluation. You only want to change the model code. And you can see I just created one more function, which was technically copy pasted and with one layer change, right? And some text change here. Generally, I even forget to do that. So that's the minimum effort you can add to really test with new models, and that's what you need. You don't want to spend a lot more time on the boilerplate code or on the other ends. And the idea going into this 5-stage ML pipeline is the same, that if you break things down vertically, you can take care of them and you can avoid repetition when you're optimizing your code, when you are trying to find the right solution. There was a piece of code which was in charge of gathering data, let's not touch that again. Let's not change it at all. I didn't make any change, right? We sort of went into a different problem. We are solving, so the problem is the same, but we went into a completely different approach. Instead of that single vector, we are taking ordered sequences, we are using recurrent neural nets, but the amount of changes that we need are really, really minimal. And that's the benefit of splitting your code into these vertical pipeline, which means that using this approach, we don't have to make any changes. We still have an optimizer criteria, and we just do, I mean, I set it to 4 some reason, but we just train it over here. It's gonna train. Since we just didn't give any data, these numbers don't make sense at all. But the process remains the same. You can just do that. You can do evaluate. You can do predict. Everything remains the same. You change the model. You change something in the data. You change something of building the data, because that was one piece of information. Instead of backwards, you wanted the index list. But these few changes, and now you have a completely different solution, right? So that's the approach I would recommend with this course. That's the approach I'm trying to teach. And that's the fast approach which you need when you're just applying ML, right? When you're building algorithms, when you're building, let's say you're building a cell for LSTM, you want to experiment with different things. So maybe even then, this kind of approach would be really, really helpful, because you want to test it through. But at least when you're applying it to a particular problem, you want to be as modular as possible. Different data set comes in, different problem comes in, gather data has to be changed, everything else, let's just keep it same, because you were not feeding in more information. All the words that you really selected were also within that data set. So different data sets have different frequencies and extremes, and you're just using that data set information. So nothing additional was provided. As minimum effort in changing as possible, and then you complete the cycle. So that's the approach we will follow. Let me quickly go over some more things to give an idea of what we'll cover next week. So this was, up till this point was ML, right? 2 weeks of machine learning completely. I've covered basics, the pipeline, and neural nets, how to use them. I will release the notebook so that you can keep on making changes in practice, try to build different model variants, keep adding more layers, see when your machine really slows down, or just keep experimenting, but change the data size, train for real. I mean, we are just doing 100, but let a larger data set come in and test it out. If for Google Colab, I'll try to add the instructions as quickly as possible, but for the data set, you will have to sign up on Kaggle and download the data from there. But if you have any other data set which you want to play around with, you can still use that. So next week, we'll again resume to the social good process. So the readings that are due for discussion on Tuesday have the social good component, and we want to cover that. And now, with the knowledge of pipeline, we will try to see how to break things down, how to analyze a problem in social good space, look at the data sources, and how do we really go forward building something on that. So I will cover some data analysis methods as well, like how to use, we used a library called pandas in the notebook to load the data, but up till here, we just really loaded the data. I mean, nothing more than that. But there are many more features within that library, which you can use to analyze data as it comes in. Our data was just sentences, but data can have way more parameters, right? Graphics data has its own parameters, and if you have, so there's a sample data set by Google, which is California housing prices. That data has a large number of features. So how can you analyze the data before going into the ML process? That's something we'll cover. And then project title, abstract, and team selection. Everything is due on 26th, Friday. But for team selection, I'm assuming you would need time in the classroom to interact with different people. So we can allocate some time on Tuesday so that you have remaining week to decide. So Tuesday, it would be better if everyone is in the class. Whoever is on the webcast right now, please come to the class on Tuesday so that we can have a bigger discussion overall on the readings. For reading discussion anyway, everyone has to be in the class because we don't have the Zoom feature where we are not using audio from Zoom participants. So please, Yeah, but then I don't know how everything will work over here. So let's everyone be in class on Tuesday, and we'll discuss the readings, more of this content, and then project.